Let's talk about latitude by meridian altitude. Well, this is the method where will be having the observation of a celestial body when the celestial body crosses observer's meridian, or this is called meridian passage. Well, this is very important from the navigator's point of view, as this provides the quick and easy method to find latitude and position line. In this video, I am going to discuss how to obtain latitude and also how to obtain position line with the observation of latitude by meridian altitude. Now, this is a simplified diagram and this is horizon, and there are 4 points here: north, south, east and west. Observer is at the center. So what happens? Sun rises in the east, so sun will rise like this, maybe from here. Sun rises in the east and goes here, attains maximum value, and then sun sets here. So at some point sun is going to be, sun will be somewhere here, and this is observer's meridian. This is observer's meridian. Why? Because it is passing through observer's zenith. So this is the point where the sun attain, and by the way, here the celestial body considered is sun only. So the sun attains maximum altitude. That means the zenith distance is minimum zenith distance. Well, let me just define. This angle is altitude and this angle is zenith distance. So since it is passing through the meridian, the zenith distance is called meridional zenith distance, right? So here in the next slide I am going to discuss more in detail. Well, suppose this is Earth and this is north celestial pole and this is south celestial pole. Well, suppose this was the equator. So the projection of equator is called equinoctial, and it is given by this. So suppose observer is here, so 90 degree to observer is called zenith, then 180 degree point is called nadir. Then we will be having one great circle. Of course, I have shown this great circle with the straight line, but this is going to be a sort of great circle like this, which is passing through the center of Earth and 90 degree away from zenith and nadir. That is called a rational horizon, right? So although I am trying my best to make it a bit simple, but the best way is to understand this whole diagram with the help of this rational horizon diagram, right? So in this, what is happening? This circle north, east, south, west, this represent the rational horizon, right? Now if you see carefully, there will be north point and then there will be pole here. So let me just mark here. There will be pole and there will be zenith. So here there will be north point, then there will be pole and there will be zenith. And this is Q, by the way. So this fellow is Q. And the south pole, obviously this is below the rational horizon, which is not visible. So that south pole cannot be seen. Actually we call it as depressed pole. And here the north pole is visible, and here also the north pole is visible. We call it as elevated pole. Okay. Of course, you need to, we have already covered this in celestial navigation, but here we need to discuss it just to understand this latitude by meridian altitude concept. So in this diagram, the latitude is represented by QZ. QZ represents latitude. Why? Because this is equinoctial and this is observer. So, similarly here this is equator and this is observer. So, this fellow, this is called latitude and it is represented here like this. Okay. Now, let us move on. Now, suppose the declination of the sun is here. So, q to x is the declination. So, the sun is going to move like this. Basically, this is the movement of sun in 24 hours. So, here the sun is rising and here sun is passing over the meridian and here this is sun is setting, and of course, the other anti-meridian thing you cannot see because sun is going to take full round. And by the way, that is the apparent motion of sun because the celestial sphere is rotating, because the earth is rotating west to east, then celestial sphere which contains the sun as well appears to be moving like this, right. So, this is theoretical rising, this is theoretical setting and this is meridian passage. So, now coming back to this, if we see carefully, this z to x, is meridional zenith distance. This is meridional zenith distance. And when the sun passes over the x, that is called meridian passage or culmination. Now, if we see n to x, this is going to be true altitude and q to x is going to be declination. So, well, this gives me a very interesting relationship that if I add this fellow and this fellow, then I can get this one, which is nothing but latitude. So, latitude can be obtained by adding declination and meridional zenith distance. Of course, let me just simplify it further with this example. Suppose declination is 10 degree north and meridional zenith distance is 20 degree north. So, here this is q, which is equinoctial, this is 0 degree. Now, the declination is 10 degree north. So, from q to x is 10 degree north. This is 10 degree north, right. The upper side, if you go up, this is north side, this is south, this is east and this is west. Now, meridional zenith distance, and that is given from x to z. Actually, x is the celestial body and z is the observer. So, from celestial body to observer x to z, that is 20 degree north. So, obviously, from equinoctial to the observer is going to be 10 plus 2, that is 30 degree north. Now, coming back to the bearing, as an observer you are here, then you will see the sun is on your south. So, bearing of the sun is 180 and meridional zenith distance, naming that means the bearing is south here. So, the meridional zenith distance will have north, naming as north, because that is always named, meridional zenith distance is always named opposite to altitude or opposite to bearing. All right. Now, let us do another example. Suppose here the declination is 10 degree north. So, here this is q and q to x, this is 0 degree and q to x is 10 degree north. So, you need to go up. So, the sun is here at the declination. Now, meridional zenith distance is 20 degrees south. So, from here you need to go 20 degrees south, 20 degrees south. So, that means from here to here this distance will be 10 degree and the latitude will be 10 degrees south. Well, if you see the bearing, then we can make out easily that the bearing is going to be, yes, as observer here, you are here and you see the sun here, the bearing is going to be north. And opposite of the bearing is meridional zenith distance, the name of the MZD. Well, the bearing is north, then MZD is south here. Now, let us move on to another example, which is example 3. So, here the declination is 10 degrees south and meridional zenith distance is 20 degrees south. So, here this is Q, which is 0 degree. Now, the declination is 10 degrees south. So, here it is 10 degrees south and you come here. Now, the sun is here. Now, meridional zenith distance from x to z, that is again 20 degrees south. So, the latitude is going to be from here to here is 30 degrees south. Now, coming back to the bearing, from here you will see that the sun is in the northerly direction. So, the bearing is 0, 0, 0 degree. Now, let us move on to another example, which is example 4. So, declination 10 degrees south and meridional zenith distance is 20 degree north. So, here Q is 0 degree and the declination 10 degrees south. So, here it is 10 degrees south, but meridional zenith distance is 20 degree north. So, from here you go up by 20 degree north. So, so from equator it is going to be only 10 degree and the direction will be north. Now, coming back to the bearing, observer is here, then you see the bearing is southerly or 180. Right. Now, let me have another example, which is example 5, and this is the last example. So, declination is 20 degrees south. Declination is 20 degrees south. So, this is Q and this is 20 degrees south, well, from here to here. But meridional zenith distance is 10 degree north. So, from x to 10, this is 10 degree north. So, you go up here. So, the difference is 10 degrees south and the bearing is 180 degree 2. So, now we have thumb rule and it says if the declination and meridional zenith distance are having same name, then you do nothing but add and retain the name. Add and retain the name, right? And if they are having different name, if they are of different name, then subtract and retain the larger name. Retain the name of larger one. So, by this way you can name the latitude. Now, coming back to another term which is called position line. So, the position line is abbreviated as PL or line of position. So, what happened here? Suppose this is a lighthouse here. So, you can take the position of the ship with the bearing. If this is the bearing, then the position of the ship is going to be somewhere here on this bearing line. Now, if you know the range, then the ship will be somewhere on this position circle, on this arc. Well, this arc is called position circle. Okay. Now, let me define some more interesting term from celestial navigation point of view, and that is called geographical position. Well, suppose this is a celestial sphere and this is Earth. Well, both the spheres, that means the Earth and the celestial sphere, both are having same center. Both are concentric, and celestial sphere will be having the radius as infinite. So, if I join a line from the center of Earth to the celestial body, then it is going to meet at the surface of Earth at some point. So, that means whatever is the position of the celestial body is in the sky, you can have equivalent position of celestial body on the surface of Earth, and that is called geographical position. Well, there are various methods how to locate this geographical position in terms of latitude and longitude. So, now what I do, I have replaced this lighthouse. This was the lighthouse. One second. This was the lighthouse. I have replaced this lighthouse with the celestial body whose geographical position we have calculated. Now, this line of position is also called celestial line of position, or CLOP. So, in this position circle, what I do, because the position circle, the radius is very large, very large on the surface of Earth. So, what I do, instead of drawing the whole circle, I draw a tangent to the position circle, and well, this tangent is going to be 90 degree to the azimuth or zenith distance. All right. So, zenith distance is the distance from celestial body to the observer, CB or X to Z. So, this is CB, this is observer. So, that is actually zenith distance. Now, how to obtain latitude by meridian altitude? Well, azimuth of bearing of celestial body is either north or south, that we have already established. Well, this is equinoctial here. Suppose observer is here, then celestial body is either north or south. So, azimuth of the celestial body is going to be either north or south. Obviously, the position line is 90 degree to north or south. So, it is going to be east or west, or 090 to 270 degree. That is the direction of latitude by meridian altitude. I mean, that is the direction of a position line obtained by latitude by meridian altitude method. Now, we need to study one more aspect, that is the time of meridian passage. Well, this time of meridian passage is approximate time, and that is given in the almanac. If you see this almanac, and at the bottom it is sun and moon. So, here this is sun and this is moon. Now, for 3 days, 19, 20th and 21, it is tabulated, and here you can easily locate the meridian passage time, which is 12, 11, 12, 11, 12, 11 in this case. So, what we do, we find LMT, which is approximate local mean time for meridian passage in terms of days, hours, minute and second. Then we apply longitude in time, that means whatever is the longitude, we just divide it by 15 and we convert into hour, minute and second. And we follow the rule longitude east, GMT least. So, in case of east, you subtract, or longitude west, GMT best, so you add in case of west, in case of east, and then we obtain the GMT value. Now, from almanac we also obtain declination. Well, with this method, this is only the approximate meridian passage. Well, but this is good enough. Let me just re-emphasize that this is good enough for the accuracy, as rate of change of declination for the approximation can be neglected. That means the declination is not going to change much, and we can take this value only. Otherwise, there is a different method to calculate meridian passage time, which will be dealt in a different video. So, now the next method is to obtain meridional zenith distance. So, here we know it very well, sextant altitude is observed, and then we need to apply index error on the arc and off the arc. If it is off the arc, you got to add, and if it is on the arc, you got to subtract. Then we find observed altitude. Then we apply dip correction. For that dip correction, let me show you here. This is the table A2, and in this table A2, you see there is a dip table, and you fill this. You just have to look from the height of I, say 5 meter. So, here it is minus 3.9. Well, the sign is already stated here, so you don't have to remember, but otherwise you should know that the dip correction is always subtracted. Now, the second part, after that applying the dip correction, you obtain apparent altitude. Then you apply total correction, and the for total correction you got to enter the same table. And if you see carefully, there are two columns, October to March and April to September. So you need to see from whatever month, whatever the date is there, and then whether you are in this column or whether you are in this column. So if whatever column you are following, then you have to see whether it is lower limb or upper limb. So in case of lower limb, you got to add, and in case of upper limb, you got to subtract the total correction. So lower limb and upper limb, after applying total correction, you get true altitude, and then 90 degree minus you get meridional zenith distance. And of course, naming of the meridional zenith distance is opposite to bearing or opposite to altitude. So now let's solve this problem. That will clear all the concepts. So here on 1st May 2008, well, it is very important to note down the date. In DR longitude, well, latitude is not given. The observed altitude of sun's lower limb on the meridian was 64 degree 35.9 south of the observer. If height of eye was 15 meter, find the latitude and position line. So here sextant altitude is not given, index error on the arc of the arc is also not given. Directly you have observed altitude, and that is given as 64 degree 35.9 minute. Now height of eye is 15 meter. So I got this almanac, and this is the column for height of eye, and if I see here between 14.7 and 15.1, I have this value as 6.8. So let me just go here, that is dip correction, and this is minus 6.8. So I get apparent altitude, and this apparent altitude is 64 degree and 29.1 minute. Then we need to have total correction, and well, total correction is for lower limb. So again I need to go back here. The date is May, so need to check in the second column, April to September, and the value is 64 degree and 64 degree 29.1. So let me just go back here. 64 degree, that means from 61 to 67. Yeah, so the correction here is plus 15.5. So let me just minimize here. The correction is plus 15.5. Why we have taken plus? Because this is the correction for lower limb. Let me just show you again. This is the correction for lower limb here. This is also lower limb, and the date here is from April to September. All right. So now we need to find true altitude, and all you have to do, just add together. That is 0.6, and this is 44, and this becomes 64. All right. So if I subtract from 90 degree, that means this becomes meridional zenith distance, and the meridional zenith distance will be 25 degree 15.4 minute. Well, the naming and all we shall see later on. Now first of all, we need to find local mean time of meridian passage. For that, we need to open again the page for 1st May. So, let us come here and we just move on. So, if you see here, this is the page for 30th April, May 1 and 2, and if you see here, for 1st May, the meridian passage time is given, which is 11 hour and 57 minute. So, here LMT meridian passage Mer pass is given, which is 11 hours and 57 minute. Well, second, let's put 00 and the day wise is 1st and the month is May. Now, let me just find out LIT, longitude in time, and this longitude is time is east. So, here for obtaining longitude in time, what I need to do, just use the calculator, okay, and this says 1, okay, just 179 degree and 58 minute divided by 15. So, we get 11 hour 59 minute 52 second. So, this is 11 hour, oh just a minute, that gives trouble, 11 hour, okay, I think I need to just minimize this program. This gives 11 hour 59 minute and 52 second. So, we know it that longitude east GMT is least. So, we need to subtract GMT. Now, if I need to subtract GMT, I cannot subtract because this is 59, this is 57. So, what I need to do, I need to borrow just 24 hours from here, 24 hours. So, that becomes 30th and the month changed to April. So, here I write April and this is 30th. Now, this is 11 and 24 hours. That time I think I should show you the working with the calculator. So, basically it was 11 hours and 57 minute. You got to add plus 24 hours here. So, you got this value 355700 minus, you have to find 11 hours 59 minute and 52 second. So, you got this value 23, 57 and 8 second, 23, 57 minute and 8 second. So, this is the GMT and the month is now April. What you have to do, you got to again go back here, and if you see in the month of April, just check the declination. If you see month of April and 23, the declination is given, which is north 15 degree 6.9, and if you see this declination is increasing, so it is increasing to the extent that the D correction is 0.7. So, let me just write here declination is 15 degree 06.9 minute north and the D correction is 0.7. Now, you got to look the increment table, and the increment table will be for 57 minute. So, in the for 57 minute, and then you need to check with 0.7. So, let me just scroll it up a little bit, and we arrive at this 57 minute. So, in the 57 minute, if you see the column, this 0.7 you have the correction as 0.7 here. So I apply this 0.7 again, and as we had observed that it is going to increase, so I put a plus sign. Then we obtain declination as 15 degree 07.6 minute north. Now it is the time to analyze. First of all, it says that the sun was south of observer. So that means this was south. So meridional zenith distance is going to be north, opposite. So what is the value of latitude? Well, by thumb rule, what you have to do, just add together. So latitude will be just sum of the two, and let's find out what is going to be the latitude. Okay, I think I can write it here also. Declination is 15 degree 07.6 minute north. So this, to sum up, we get the value as 23 north, and this becomes 40 degree. That is the observed latitude. Now to analyze it, what I'll do, I'll draw the simple diagram, and here suppose this is equinoctial, this is equinoctial 0, then declination is 15 degree, so this is Q, and then the declination is 15 degree north, so this is X, this is 15 degree north, and then meridional zenith distance is 25 degree north. So X to Z, that is also north. So the total latitude is going to be this one, which will be the sum of declination and meridional zenith distance. So another thing, the position line is going to be east and west, and that is the answer of this problem.